Before I get into this, I need to correct the premise of that headline directly, because the actual news is almost the exact opposite of what it implies. Voyager 2 did not send back a final warning, and it is not going silent. Just days ago, NASA's own engineers announced they had successfully pulled off an experimental, never-before attempted power maneuver specifically to keep Voyager 2 talking for at least another year, buying time for all 3 of its remaining instruments right when the spacecraft was genuinely about to lose one of them for good. This is the real story of what actually happened to Voyager 2 this month, why NASA nicknamed this specific engineering effort the Big Bang, and what the honest, current timeline actually looks like for when this 49-year-old spacecraft might eventually fall silent for real. If you want accurate space reporting instead of manufactured doom, subscribe now, because the true story here is considerably more impressive than the exaggerated version. Let's start with where Voyager 2 actually stood before this announcement, because understanding the real stakes requires understanding the genuine ongoing power crisis both Voyager spacecraft have been managing for years now. Voyager 2 launched on August 20th, 1977, 16 days before its twin, Voyager 1, and took a longer, more complex trajectory through the outer solar system, becoming the only spacecraft in history to fly past all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, in a single mission. Both spacecraft get their electrical power from radioisotope thermoelectric generators, devices that convert heat produced by the natural radioactive decay of plutonium-238 into usable electricity. That power source has no way to be refueled or replenished, and it has been steadily, predictably shrinking by roughly 4 watts every single year since both spacecraft launched. A slow, mathematically certain decline that has no workaround, only management. Each Voyager spacecraft originally carried 10 separate scientific instruments. Over the decades, as the mission moved past its planetary flybys and eventually into interstellar space, engineers have had to progressively shut down more and more of those instruments, simply to keep the spacecraft themselves alive and transmitting, prioritizing the specific instruments considered most valuable for studying the heliosphere and interstellar space, generally referred to as the fields and particles instruments, over everything else. That process has been steady, deliberate, and largely non-negotiable, dictated entirely by the unforgiving math of a shrinking power budget, rather than any choice about which science the team would prefer to keep running. If a story built on real, verified NASA and JPL reporting instead of manufactured doom is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. Here's the actual sequence of shutdowns that's brought both spacecraft to where they stand right now, because the timeline itself tells the real story considerably better than any single dramatic headline could. Voyager 2's plasma science instrument was switched off in September of 2024. Voyager 1's cosmic ray subsystem followed in February of 2025. Voyager 2's low-energy charged particles instrument was shut down the following month, in March of 2025. And Voyager 1's own low-energy charged particles experiment, an instrument that had been running almost continuously since the spacecraft's 1977 launch, was finally shut down in April of 2026. Every single one of those commands had to travel across a communication delay now stretching between 20 and 23 hours each way, and every shutdown has been treated by the mission team as potentially permanent, since there's no way to send a repair mission or reactivate hardware that's failed at a distance of billions of miles. That sequence left Voyager 1 down to exactly 2 functioning science instruments, a magnetometer and a plasma wave subsystem. Voyager 2, thanks to its slightly more favorable power situation, had been sitting 1 instrument ahead of its twin, still running 3, its own magnetometer and plasma wave subsystem alongside a cosmic ray subsystem. But according to NASA's own reporting, without some kind of intervention, Voyager 2 was on track to lose that 3rd instrument before the end of 2026 as well. Another routine, unavoidable casualty of the same steady 4-watt-a-year decline that had already claimed 4 other instruments across both spacecraft over the preceding 2 years. If you found this level of detail more useful than the original headline suggested, drop a comment and let me know. It genuinely helps me figure out what to cover next. That's the specific crisis engineers at NASA's Jet Propulsion Laboratory were actually trying to solve, and on August 4th, 2026, just days before this video was made, they announced they'd genuinely pulled it off. The procedure, internally nicknamed the Big Bang, involved something considerably more ambitious than any previous power adjustment attempted on either spacecraft. Rather than a simple one-for-one swap of a single powered device for a lower power alternative, the kind of adjustment the team had made periodically in the past, this specific maneuver required simultaneously switching off a whole set of powered devices across the spacecraft and substituting them with lower power alternatives all at once, while carefully ensuring Voyager 2 remained warm enough throughout the entire process to continue operating normally. A spokesperson for the mission specifically noted that previous power swaps had generally been simple one-to-one substitutions, making this coordinated multi-device version of the procedure a genuinely new kind of engineering challenge for a spacecraft this old. According to NASA's own Voyager blog, the Big Bang procedure directly resolved the exact threat facing Voyager 2's cosmic ray subsystem, the instrument that would otherwise have needed to be shut down before the end of this year. As a direct result, all three of Voyager 2's remaining science instruments are now expected to keep running for at least one additional year beyond what would have otherwise been possible. That's not a small technical footnote. It represents genuinely new, previously unplanned time for an interstellar science mission that has already outlived its original design lifespan by roughly 44 years, still gathering real, scientifically valuable data from a region of space no other operating spacecraft has ever sampled. If you found this success story as encouraging as I did while researching it, drop a comment and let me know. It genuinely helps me figure out what to cover next. It's worth understanding exactly why engineers chose to test this specific, higher-risk procedure on Voyager 2 first, rather than on its twin. Voyager 1 sits considerably farther from Earth than Voyager 2, meaning every single command sent to it and every confirmation sent back. It takes even longer to complete that already lengthy round trip. Voyager 2's slightly more favorable position, combined with its slightly larger remaining power margin, made it the comparatively safer spacecraft to test an entirely new, previously unattempted power reconfiguration procedure on, precisely because a failed attempt on Voyager 2 would have been marginally less catastrophic to recover from than the same failure occurring on its more distant twin. With Voyager 2's test now confirmed successful, NASA's engineering team has indicated plans to attempt the same fundamental procedure on Voyager 1 in the coming months, hoping to buy similar additional time for its own two remaining instruments. There's real, candid uncertainty baked into how NASA itself describes this entire effort, and it's worth including that honesty directly rather than glossing over it, because it's precisely the kind of detail a manufactured final warning headline tends to erase in favor of pure drama. Engineers involved with the mission have been explicit that, while they believe keeping at least one science instrument running on each spacecraft into the 2030s remains genuinely achievable through careful, continued power management, nearly 49 years of continuous deep space operation has exposed both spacecraft to genuinely unpredictable conditions that could, in principle, produce an unforeseen failure at any time, entirely independent of the steady, predictable power decline this video has focused on. That's an honest acknowledgement of real uncertainty, not a dramatic warning of imminent silence, and the distinction between those two things matters enormously for understanding where this mission actually stands right now. It helps to understand a bit more about that specific plasma wave discovery because it's a genuinely good illustration of exactly why keeping these two particular instruments alive matters so much to the broader scientific community. Both spacecraft's plasma wave subsystems rely on two long antennas, extending roughly 10 meters, about 30 feet, out behind each spacecraft in a V-shaped configuration engineers have informally nicknamed the bunny ears. As the extremely sparse plasma filling interstellar space oscillates, those antennas pick up the resulting electric field fluctuations directly, and the specific frequency of that oscillation corresponds mathematically to the density of the surrounding plasma. Voyager 1's own data, once Ocker went back through it carefully, revealed a nearly continuous version of this oscillation that had simply been hiding in what everyone had assumed were uneventful gaps between rarer, more dramatic solar events. Researchers still haven't fully determined the precise physical mechanism producing that persistent signal, whether it reflects ordinary thermally excited plasma oscillation or a related but distinct phenomenon called quasi-thermal noise, a genuinely open question that depends directly on both spacecraft's plasma wave instruments continuing to function for as long as possible. It's worth understanding a bit more about the two specific instruments both spacecraft are now down to, or close to being down to, because they weren't chosen arbitrarily. The magnetometer aboard each spacecraft measures the magnetic fields present in interstellar space, data that's helped researchers understand how our sun's own magnetic influence interacts with the wider galactic environment surrounding our solar system. The plasma wave subsystem, meanwhile, is responsible for one of the single most remarkable discoveries either spacecraft has made since crossing into interstellar space, detecting a persistent, nearly continuous oscillation in the plasma filling the space between stars, first properly identified by researcher Stella Ocker after she noticed the pattern sitting quietly in data that had previously been dismissed as uneventful background noise. That specific instrument remains genuinely scientifically active right now. Still gathering data, researchers haven't fully finished interpreting, which is a significant part of why keeping it running for as long as possible on both spacecraft has remained such a consistent priority throughout every round of difficult shutdown decisions the mission team has had to make. It's worth remembering exactly what Voyager 2 actually accomplished before it ever reached interstellar space, because that history is part of what makes every additional month of continued operation feel genuinely significant to the scientists who've spent careers studying its data. Voyager 2 remains to this day the only spacecraft in history to have visited Uranus, and during its January 1986 flyby, it discovered 10 previously unknown moons, 2 new rings, and measured a magnetic field so strangely offset from the planet's own rotation axis that it still challenges models of how planetary magnetic fields form in the first place. It also remains the only spacecraft ever to visit Neptune, and during its August 1989 flyby, the final planetary encounter of the entire Voyager program, it discovered 6 new moons, measured supersonic winds reaching 2,400 kilometers per hour, and captured detailed images of Neptune's largest moon, Triton, revealing active nitrogen geysers and strong evidence that Triton was originally a captured Kuiper Belt object rather than a moon that formed alongside Neptune itself. Every one of those historic achievements happened using the exact same aging hardware currently being kept alive through careful power management nearly 4 decades later, a genuinely remarkable testament to how durable this specific engineering actually turned out to be. Suzanne Dodd, Voyager's project manager at JPL, has described both spacecraft in fairly affectionate terms befitting a mission she's helped guide for years, referring to them as deep space rock stars, while also being direct about the underlying math driving every one of these decisions. Ahead of an earlier round of shutdowns, she explained plainly that if the team hadn't turned off an instrument on each spacecraft at that specific point, both probes would likely have had only a few more months of power left before the mission would have had to formally declare its own end. That's the actual honest stakes involved in decisions like the Big Bang procedure, not a single dramatic warning message, but a continuous, carefully managed balancing act between squeezing out every possible extra month of real science and the hard physical limit of a power source that simply cannot be replenished, no matter how carefully it gets managed. It's worth putting the actual engineering risk of this specific procedure in context, because coordinating a simultaneous swap of multiple power-consuming devices on a spacecraft this old carries real, non-trivial danger that's easy to understate. During any power system reconfiguration, there are brief transitional moments where the spacecraft sits neither fully in its old configuration nor fully in its new one, and those transitional moments can potentially trigger automated fault protection systems, safety mechanisms built into the spacecraft specifically to begin shutting down components on their own if they detect power draw exceeding what the aging generators can currently supply. Executing several changes simultaneously, rather than one at a time, is specifically meant to minimize how long the spacecraft spends sitting in that vulnerable transitional state. But it also means there's less opportunity to catch and correct a single failed step before moving on to the next one. A team member involved with the mission was candid about the tension involved in sending a command that ambitious across a distance requiring more than a full day just to learn whether it had actually worked. An entire team essentially holding its breath together, waiting to discover whether Voyager 2 would come back online exactly as planned, or whether something in that carefully coordinated sequence of changes had gone wrong in a way nobody could immediately fix from more than 12 billion miles away. It's also worth remembering just how far both of these spacecraft actually are, because the scale involved is easy to state as a number and considerably harder to actually internalize. Voyager 2 currently sits more than 12 billion miles from Earth, deep in interstellar space, a region beyond the direct influence of our Sun that only one other human-made object, Voyager 1, has ever reached. Every single command sent to adjust something as delicate as this recent power reconfiguration had to be calculated, transmitted, and confirmed across that entire distance, with engineers on the ground having no way to intervene in real time if something began going wrong partway through the procedure. Successfully executing a genuinely new, previously untested maneuver under those conditions, on hardware that predates the personal computer, represents a real, substantial engineering achievement in its own right, independent of whatever specific scientific data these instruments continue to gather in the months ahead. There's a piece of the broader Voyager story worth including here too, because it connects this recent engineering success to the much longer history behind it. Ed Stone served as the Voyager mission's chief scientist for decades, having guided the program through its original planetary flybys of Jupiter, Saturn, Uranus, and Neptune, all the way through both spacecraft's eventual crossings into interstellar space. Stone was directly involved in helping the public understand exactly how transformative those early discoveries actually were, once noting that Voyager revealed just how complex and dynamic the solar system genuinely is, at a time when active volcanic activity, later discovered on Jupiter's moon Io during Voyager's own flyby, had never before been confirmed anywhere beyond Earth itself. Stone retired from that role in the years before this recent Big Bang announcement, but the careful, deliberate approach to squeezing every possible additional month of science out of two aging, irreplaceable spacecraft, exactly the approach on display in this month's successful power maneuver, reflects the same basic philosophy he helped establish over his own decades leading the mission. There's a broader point worth sitting with as this story wraps up too, one that extends past the specific engineering success covered throughout this video. Both Voyager spacecraft carry a golden record, a gold-plated copper disc containing greetings in 55 human languages, sounds from Earth, and a map showing their exact point of origin, intended to persist and remain physically intact for potentially billions of years after either spacecraft finally stops transmitting for good. Every additional month of instrument operation that engineers manage to squeeze out through efforts like the Big Bang procedure represents real, ongoing scientific data gathered before that eventual silence arrives. But it's worth remembering that even once these instruments do finally go quiet, whether that happens next year or sometime in the 2030s, both spacecraft themselves will simply keep moving, carrying that same record outward through interstellar space for a length of time that dwarfs the entire history of human civilization. The engineering effort covered throughout this video isn't really about preventing that eventual silence altogether, since nobody involved with the mission has ever claimed that's possible. It's about making sure that whenever that silence does finally arrive, it comes only after every last possible month of genuine, irreplaceable science has actually been gathered first. Looking ahead, the real story worth watching now is what happens when engineers attempt this same Big Bang procedure on Voyager 1 sometime in the coming months. An attempt carrying somewhat higher stakes given Voyager 1's greater distance and its already reduced count of 2 remaining instruments. If that attempt succeeds the way Voyager 2's test just did, both spacecraft would enter the back half of this decade with genuinely renewed operational margin, pushing the realistic possibility of at least one working instrument on each spacecraft surviving into the early 2030s, from a hopeful long-term goal into something considerably closer to an achievable, actively pursued outcome. If it doesn't succeed, Voyager 1 would likely lose one of its 2 remaining instruments sooner than currently planned, leaving the spacecraft down to a single working sensor earlier than the team would prefer. Either way, the outcome of that attempt, whenever NASA formally announces it, will matter considerably more to the actual future of this mission than any single dramatic headline could capture on its own. So, what does all of this actually add up to? Voyager 2 did not send back any kind of final warning, and it has not gone silent. What actually happened, confirmed by NASA just days before this video, is that engineers at the Jet Propulsion Laboratory successfully completed a genuinely new, previously untested power management procedure, coordinating a simultaneous swap of multiple power-consuming devices for lower power alternatives, specifically to prevent the exact kind of instrument shutdown that had already claimed 4 other instruments across both Voyager spacecraft over the preceding 2 years. That success buys Voyager 2's 3 remaining science instruments at least 1 additional year of operation, and it sets up a similar attempt on Voyager 1, currently down to 2 instruments, sometime in the coming months. Both spacecraft remain genuinely fragile, operating on hardware nearly 49 years old with a power supply that continues shrinking by 4 watts every single year with absolutely no way to replenish it. And engineers themselves are honest that an unexpected failure remains a real, if currently unrealized, possibility at any point. But the actual news this month isn't a warning of impending silence. It's confirmation that the team responsible for keeping these 2 remarkable, irreplaceable spacecraft alive just found a genuinely clever way to buy them more time, using an entirely new engineering approach on hardware that was never designed or expected to still be functioning nearly half a century after it first left Earth. If stories like this, the accurate version, rather than manufactured doom, are what you come here for, subscribe to this channel and turn on notifications. Because both Voyager spacecraft are still out there, still transmitting, and there's a very real chance the same Big Bang procedure that just worked on Voyager 2 succeeds on its twin in the months ahead as well. Thanks for watching, and I'll see you in the next one.